So our last skill here in electrochemistry kind of pulls a lot of things together. Remember, in skill 1, we learned how to write and balance redox equations. In skill 2, we learned how to diagram a voltaic cell. In this third skill, we're going to learn how to calculate the potential of that voltaic cell. And we're also going to then connect lots of pieces together here and think about how this relates to the free energy of a process and then also the equilibrium constant. So kind of pulling this all together here. So cell potential. What is cell potential? Well, cell potential refers to the energy available to do work of moving a charge between electrodes. So it's really what's the charge on the battery, right? You've got a AA battery, right? It's going to be 1.5 volts. Okay, so how do we calculate that, right? So we're going to go through the math for how you calculate that. So this is what we call standard cell potential, or Ecell. And it's measured, again, at a specific temperature, often 298 K. That we've got all our components in the standard state, 1 atmosphere for gases, 1 molar solutions, pure solids for our electrodes. So we've got some standard conditions, which is why we see that standard symbol. Okay, standard half cell potentials are just the potentials for the half reactions, right? And what we tend to see them written as are reduction reactions. So electrons on the left, the gain of electrons. Okay, so what we have here is the standard reduction potential for zinc, and then here's the standard reduction potential for copper. This is this reaction that we've been kind of carrying through as a thread here, this zinc copper battery we talked about, and then we had the zinc copper half cell reactions that we balanced in our first skill. But if we've got a redox reaction, we know that something has to be gaining electrons, but something else must be losing. Maybe you remember here, we knew that zinc was going to be the one that lost electrons. But we can actually do some calculations here to show why that is the case and why that direction is the spontaneous reaction for this redox process. So this all has to do with the last appendix that we're going to have as part of some reference data that we'll use for calculating problems here. And this is Appendix D. Appendix D is a list of standard reduction potentials. So what we're going to see, this is sort of a short version of this list right here. We're going to see that there's something in the middle here that is 0. This is the standard hydrogen electrode, sometimes referred to as SHE. We just define this as a middle point as being 0. And certain things have larger standard reduction potentials or smaller and more negative standard reduction potentials. Okay, so we're going to use this table a lot, just like we used Appendix B for our thermodynamic parameters. So how are we going to use this table and how are we going to calculate Ecell? So a couple of things I'm going to highlight here is I'm going to teach you a method that may be different from a method that you've already learned. I'm fine with you continuing to use that original method. Maybe it's something that you learned in high school. That's fine to use as long as it gets you to the right answer. I am going to do something that's often different from what is in many textbooks. Both ways will always give you the same answer, but I'm going to share with you why I think my way makes a little bit more sense. Okay, it's different from what the standard is in the electrochemistry field. So sorry to my electrochemistry colleagues out there. I know this is going to be different than the formalism, but I truly believe that this is the easiest way to arrive at the right answer. So this is the strategy that I'm going to be teaching you guys. If you already know how to do something else, feel free to just kind of mute and ignore the rest of this. But if this is new to you, or if maybe you don't remember how to do something, I want to teach you a strategy here. Just like we've done with lots of our other problems, I'm not going to read through all of these steps here. These steps, as always, are available in the accompanying notes for these videos. But I'm going to run through them briefly, and then we'll implement them as we do a problem. The first step is you have to write half reactions for what's happening. So this builds on our first skill of writing and balancing half cell reactions. So for some species, you might know who's oxidized or reduced. If not, write everything to start as a reduction reaction. Then we're going to find some values in Appendix D for the standard reduction potential for each of those half reactions that we wrote as reductions. Remember, this Appendix D is going to have everything written as half reactions that are reductions. So we're going to write both of them. Unless you know, write both of them as reduction reactions and write the values that we get from Appendix D. Okay. The third step is to scale the equation as needed for the number of electrons that are lost. Remember, we did this when we were balancing our chemical equations, right? If we had an unequal number of electrons that were being given up in the oxidation reaction versus taking in the reduction reaction, we had to scale those reactions so we had equal numbers of electrons being given up and taken in, okay? This is where things can get confusing. When we scaled equations, when we did things like Hess's law and stuff like that, we scaled the delta H or the delta G values, or we manipulated K values when we were doing things with equilibrium constants. We do not scale anything here. Highlighting in red, do not scale this. We need to scale things from the coefficient standpoint, so we have the right number of electrons and we'll have a balanced overall reaction, but you do not scale the standard reduction potential values. So highlighting that. Classic place that students make mistakes. Then we're going to sum up the equations. Now our electrons should cancel just like when we were balancing half cell reactions, okay? And what we're going to do here is we are going to sum the equations so that they cancel. Oh, and a really important part that I kind of highlighted here. If something is going to be an oxidation reaction, we're going to use the negative of the value that's on the table. Okay, so we're writing both of these as reductions, but one of them is going to be needed to be used as an oxidation reaction. Okay, we're going to flip that reaction. If we don't know which is oxidation and which is reduction, flip and reverse the sign of the one that allows you to have a positive Ecell. This is the key part here. A spontaneous reaction has a positive Ecell. This is different from delta G. Delta G, if it was spontaneous, was negative. Delta E, if it's spontaneous, is positive. That's an important thing we need to make sure that we remember. Delta E is positive for a spontaneous redox process. Okay, so a couple of problems we're going to kind of work through here. Okay, so we're going to calculate Ecell when we're in a system where we already know our half reaction. So maybe you're given a voltaic cell, or you've diagrammed a voltaic cell, or you're given shorthand notation. So you know what's on the left, you know that's the anode, you know that's where oxidation occurs. So maybe you have some information that's already known. So let's go through and calculate Ecell for this process. So let's sort of start with our first kind of process that we've spent a good bit of time learning about, this zinc copper voltaic cell. This is the one that we first learned how to diagram in our last lecture. And in it, we learned that the zinc compartment is going to be our anode, so that's where oxidation occurs. So I'm going to go ahead and write an oxidation reaction here. I'm going to show you on the next slide here, this would be a negative 0.76 if we saw it on Appendix D, because this reaction would be reversed. Okay, but this is the standard reduction, or the standard potential that we have here for this oxidation reaction. For the copper, which we know is a reduction reaction, that value on the table is 0.74 volts. When we add both of these up, we can see that we get an overall positive Ecell. So remember, Ecell is really adding these two these two potentials together. And we get 0.76 plus 0.34 is positive 1.1 volts. Because that's a positive reaction, or a positive Ecell, that's a spontaneous reaction. So again, I'm going to show you here with Appendix D. So here again is the copper half cell reaction written as a reduction, right? So we can see we would use that directly as is, 0.34 there. If I try to find zinc on there, remembering that all of these are written as half cell reduction reactions. So all of these have electrons on the left. So in order to find the zinc piece, I have to find zinc 2+ gaining 2 electrons to become zinc solid. Notice that the value for this is minus 0.76. But remember, we need to flip this reaction because we need to see it as an oxidation reaction. So when we flip that reaction, we need to change the sign from what we see on Appendix D. But that's what allows us overall to sum these together and have a spontaneous voltaic cell there. We have an Ecell of positive 1.1 volts. All right, so maybe there's a process that you don't know what's going on with it. Maybe we just know that we've got a voltaic cell, but we actually need to go through the process of diagramming it to know who's on the left. So this problem right here is a little bit more involved because we're actually building all of these other skills up together. We're going to have to diagram this voltaic cell to figure out what is going on with oxidation and reduction. So this one's going to take a little bit more time to go through, but let's try working through this problem. So let's have you guys practice one here yourself, and then we're going to go through a couple of other examples here. So this first one says, we want to calculate Ecell when we have a spontaneous process in a tin silver voltaic cell. And again, they didn't give us any other information to say that we've got tin and silver. Now, if this was a problem we did in our last lecture, we would have said which electrode was positive, and that would have told us which was the cathode, or which electrode was negative, and that would have told us which was the anode. We don't know that here, but we have Appendix D. So I want you to think about this. I'm going to give you a few clues, and I want you to try this on your own. Write both of these reactions as reduction reactions, and then figure out which one you'd want to flip in order to have an overall E cell that's positive. And then the one that you use as is, that's going to be your cathode. The one that you need to flip, that's going to be your anode, your oxidation. So pause the video for a second and see if you can write down both of these reactions, write them both down as reduction reactions, and then look at Appendix D and see if you can figure out which one we might need to flip. All right, so here's the data from Appendix D. We can see if we write these both down as reduction half reactions, we're going to have the tin reaction having a negative standard reduction potential, and the silver reaction having a positive one. So now again, think about which one of these reactions do we want to flip in order for us to have a positive E cell, and then see, do we need to scale either of these reactions to make sure that we'd have an overall balanced redox reaction? So think about that, try to figure out how you'd get a net overall reaction, and then think about what that means is going to go into our voltaic cell diagram here. So first, let's just try figuring out what our overall E cell is going to be for this balanced chemical redox reaction. All right, so hopefully you quickly recognize that this is going to be the reaction that we need to flip. That's the one that has the most negative standard reduction potential, E reduction. So we're going to flip this guy. And remember, when we flip this reaction, we need to change the sign on E, and we make it an oxidation. So again, we make this an oxidation reduction or oxidation potential here, which means we change the sign. And then we actually need to leave the silver one the way it is, but we need to scale it. So we're going to scale everything up by 2 so that we have the 2 electrons in our reduction reaction that we need to cancel. So again, everything gets scaled up by 2, but we do not change the value of our standard reduction potential. That stays as is, as positive 0.8 volts. So again, we're going to sum these up to get our overall balanced redox reaction, making sure, again, our electrons cancel. That's skills that we learned in our first lecture. And then E cell is equal to the standard reduction potential plus the reduction potential that we've made into an oxidation potential. So we're going to add both of those together, and we get 0.94 volts. So what I want you to do now that we know all of this information, see if you can practice a skill from last lecture and take this information and map it onto a voltaic cell diagram. So go ahead and try that. Pause the video and see if you can figure out that solution. All right, so we knew that we were going to have our tin be our oxidation reaction, so that's going to be our anode. So we're going to have a tin electrode, and we're going to be generating tin ions in solution. So our silver kind of chemistry is going to be our cathode half cell. That's where reduction's occurring. So we've got a silver electrode. Both our electrodes are active in this voltaic cell. And we're going to have to make sure that we have silver ions in solution, because those silver ions that are in solution are going to be what are used to get reduced. Again, anions are going to flow to the anode. Cathode is going to be where cations migrate to in our salt bridge. But now we can fill in this last little piece. We know that the value of this voltaic cell is 0.94 volts. Okay, so kind of pulling in skills from all three lectures here, balancing redox equations, diagramming voltaic cells, and now importantly, figuring out the quantitative value of those voltaic cells. All right, so kind of wrapping up a few little loose ends here. Remember when we did chemistry, when we talked about acids and bases reacting, and we always had strong acids and strong bases reacting to give us weaker acids and weaker bases. And that's how we could figure out where the equilibrium lie with a process like that. Chemistry always happens to go downhill to make less reactive species. The same is going to be true here. If we're talking about which side we might have kind of be the favorable side for a process, we can look at chemistry happening to generate things that are weaker in their oxidizing or reducing potential. Okay, so we can actually use Appendix D. We can do some chemistry to sort of figure out which way that is. Okay, so remembering positive delta E values are going to show us the favorable direction for a process. All right, so let's tie this all together, learn a couple of new equations that allow us to relate things that we've learned from previous learning units. Okay, so this is not really around the block, it's more around the triangle here, but we've learned about free energy, right? We've learned about equilibrium. And in our last learning unit, right, we learned how to relate the differences between delta G and K. Okay, so this was our equation that allowed us to do that. We've got another piece to this triangle, if you will, here. Now that we know Ecell is related to delta G by this equation, and Ecell is related to K by this equation. Okay, so equations that'll be provided for you. I'm going to talk to you about what these constants are, but one of the skills that you're going to have to do is know how to interconvert these parameters. Okay, so once you have Ecell, and that was part of what we had to learn in this skill, is how we can use Appendix D and figure out Ecell. And it might rely on diagramming a voltaic cell in order to know what's going on in that process. We can then, once we know this, use one of two equations to walk to either delta G or to K. Noting here are the constants that you're going to need. The R constant is not going to be the gas constant. It's going to be the one that has energy as part of it. So it's the 8.314 joules per mole Kelvin. Here's a new constant that we haven't really talked about. This is Faraday's constant. Will be provided for you, but this is going to be the F that we see here. And then N is going to be the moles of electrons transferred. So you may need to do what we did in Skill 1 or in diagramming a voltaic cell, learning how many electrons are traded back and forth, because that N becomes part of these equations. So it's a necessary part of determining either free energy or an equilibrium constant. Okay, so all of these pieces kind of coming together from a calculation sort of standpoint. One last piece to highlight is something called the Nerst equation. So do you remember from last learning unit when we talked about thermodynamics, sometimes we said maybe we're going to be at non-standard conditions, and we had an equation that allowed us to convert delta G naught, that one at standard conditions, into delta G. We've got a same kind of equation here when we're talking about standard reduction potentials here, so Ecell. So if we are at non-standard conditions, okay, Ecell is going to have to subtract off of this piece. Okay, so what is this piece? Well, it's R that we just talked about, the temperature that we're at if we're not at a standard temperature, our N, which is the number of electrons that are transferred, and then that F, that Faraday's constant. So sometimes our non-standard conditions really just imply that we've got different concentrations of things, not 1 molar. So if that's the case, we can actually combine these pieces, R, which is a constant, if the temperature is at 298, if we're at 25 degrees C, and then that Faraday constant, we can merge them into one constant that has a specific value. Okay, so R, T if we're at 25 degrees C, and our Faraday constant can be lumped together to this. So these equations really are the same if we are at 25 degrees C. Okay? So solving a problem like this can be a little bit multi-part. So watch this. Why? Because we might need to calculate Ecell. Well, we need to determine half reactions because we need to know the N. And we need to know Q, which might mean we have a balanced chemical equation that we relate to a Q expression, and then we need to use those non-standard conditions to go in for what Q is. So there might be lots of pieces that layer in to solving this problem. Simplest way is I just sort of give you what these pieces are. All right, so why is this important? Well, sometimes we can have a voltaic cell that has the same things in the anode and the cathode. But what makes them different is we've got different concentrations. Okay, so I'm going to show you a picture of one in a minute that hopefully will make sense. But here's sort of the species of what's going on. In our oxidation half reaction, we're going to have a copper electrode that is oxidized, losing electrons and generating copper ions in solution. In our reduction half reaction, we're going to have copper ions that are going to pick up those electrons and generate solid copper. So if we add these up, it seems like everything cancels out, with the exception of, note that on our oxidation half cell, we've got copper that is going to be a low concentration, so that's over here. In our reduction half reaction, we've got copper ions that are at a high concentration, okay? But the copper ions that are at a high concentration are the ones that are being used up. The copper ions that are at a low concentration are the ones that are being generated. So what happens when we have this? Look at, and the picture here kind of gives us an indication of what's going on because copper ions in solution are blue. So look over here. We've got a low concentration of copper ions. So this is a lighter blue over here. And then we've got a darker concentration of copper over here, darker blue, higher concentration of copper. So what happens here is we're going to have this electrode kind of lose mass because these copper ions are going to go into solution, but that also makes this solution more blue. And then these copper ions are going to go out of solution, be plated out, make this copper electrode heavier. We're going to be decreasing this concentration. So this this voltaic cell will operate until these concentrations are equal. But note here, we don't start out with like this super strong voltage here. This isn't something that kind of contributes a significant voltage, right? If we think about this from a math standpoint, Ecell for this is going to be 0 because it's the same oxidation and reduction reaction. So Ecell that's under standard conditions is going to be 0. Where this voltaic cell gets its power is by these concentrations being different. So we're going to go through and there'll be some extra credit problems to work through with how you can calculate Ecell when you have non-standard conditions. Okay, so this is a little bit of a dicey chapter with sort of some intense calculations, but lots of opportunity to practice both in class and with some extra credit problems.